Hello everyone, welcome to the today's knowledge session on the topic data engineering with Databricks, presented by me Purva Agrawal and Anshika Agrawal. So, before starting, let's go through some basic knowledge etiquettes that we should follow, because lack of etiquettes and manners is a huge turnoff. So, first is punctuality. Join the session 5 minutes prior to the session start time. We start on time and conclude on time. Feedback, make sure to submit a constructive feedback for all the sessions as it is very helpful for the presenter. Keep your mobile devices in silent mode. Feel free to move out of the session in case you need to attend an urgent call, and avoid unwanted chit chat during the session. So the agenda for today's session is we'll get started with Databricks, data science and data engineering. Perform common code development tasks in a data engineering workflow using Databricks Data Science and Engineering Workspace. Use Spark to extract data from a variety of sources, apply common cleaning transformations, and manipulate complex data to load into Delta Lake. Third is define and schedule data pipelines that incrementally ingest and process data through multiple tables in the Lakehouse using DLTs, which is Delta Live tables. Orchestrate data pipelines with Databricks Workflow, jobs, and schedule dashboard updates to keep analytics up to date. And finally, configure permissions in Unity catalog to ensure that the users have proper access to database and for analytics and dashboarding. So let's first start with the first topic, get started with Databricks data science and engineering.
So what is Databricks? From the topic when we start, it comes to our mind what actually is Databricks. So it is a commercial cloud native implementation of Lakehouse model. Here Lakehouse is a data storage layer on top of data lake. It provides reliability and performance support to existing data warehouse. It proves to be cost efficient, scalable, and efficient all together at one platform. It provides a variety of data practitioners like SQL analysts, data engineers, machine learning practitioners to perform their role in a unified and scalable way. Moving on, we will learn about the Databricks architecture. The diagram here shows the architecture of the Databricks. There are three major parts of the architecture, as you can see: control plane, data plane, and cloud storage. Let us understand each one of them one by one. So to start, we will first learn about data plane. The data plane is where the data is processed. All the computer resources in specific data plane will reside in their specific cloud account only. The compute resource, you can call them clusters also, connect to data store back to the base Databricks file system. There is always an option to connect to external data sources within the cloud account or anywhere on the internet. For example, JDBC or SQL data store or data lake stored on AWS or GCS. Moving to the next part of the architecture, the control plane. It is a set of backend services provided and managed by the Databricks in its own cloud account aligned with the cloud server that are in use by the customer. That might be AWS, Azure, or GCP. The majority of data don't live here, such as notebook commands and workspace configurations are stored in the control plane and encrypted at rest through the control plane and associated user interface and APIs. It provides us the ability to launch cluster jobs and get result and interact with the table metadata. It has several services: web app, cluster manager, workflow manager, jobs, notebook, repo, TSQL, and also the Unity catalog. The web app provides the customer to access the database. Workflow manager provides job workflows and Delta Live tables or DLT to orchestrate tasks in a number of ways. A cluster manager helps set up and configure Spark clusters. Job is used to schedule the tasks. Coming to the Unity catalog. So Unity catalog is the one which provides data governance around access control, metadata management, data linkage, and data discovery. We will learn about the Unity catalog also in detail in the later part of the session. The Databricks web application delivers three different services: that cater to the specific needs of various personas, like data science and engineering persona, Databricks machine learning practitioners persona, and Databricks SQL analyst persona. Let's understand what is clusters. So a Databricks cluster is a set of computational resources and configurations on which we can run data engineering, data science, and data analytics workflows. These workflows can run a set of commands in the notebooks or a job. The clusters live in the data plane within the organization's cloud account. Cluster management is the function of the control plane that is part of the service provided by the data science platform. Yeah. So now let us understand how computer resources is capable of running all the processing workload platform. So cluster consists of one or more virtual machine instances to which computational workloads are distributed. In the standard case, cluster has a driven node alongside the worker nodes. Although Databricks provides us with the option of single node cluster also. Workloads are distributed across the available worker nodes by the driver node. As you can see in the diagram also, the diagram represents the structure of a standard cluster node here, because we have the driver instance also and the worker nodes also available. A cluster node is an operating mode of which there are two options: single node cluster and multi-node cluster. So single node cluster, it needs only one virtual machine instance hosting the driver. There are no worker nodes. It is low cost and is useful for single node machine learning workloads or as well as lightweight exploratory analysis. Standard cluster is a general purpose configuration consisting of virtual machine instance hosting the driver, and at least one worker node should be present for a cluster to become a standard cluster.
So Databricks provides us with two main types of clusters, all-purpose clusters and job clusters. So let's talk about them and understand the basic difference between them. So first of all, an all-purpose cluster. So it is a shared cluster that is manually started and terminated and can be shared by multiple users and jobs. It is used for interactive development. All-purpose clusters such as ad hoc analysis, data exploration, and development, they're designed for collaborative use. So that means that multiple users can share them, and the configuration information can be retained for up to 70 clusters and for up to 30 days. So all-purpose clusters analyze the data collaboratively using interactive notebooks. We can create all-purpose clusters from workspace or programmatically using the CLI command line interface or even the REST APIs. Now, second, the job clusters, on the other hand, they are created when the job or the task starts, and they're terminated only when the job or the task ends. It is used for basically automating the workloads. They are specifically for running automated jobs in a robust way. So we cannot restart a job cluster, and the configuration information is retained for up to 30 recently terminated clusters. So let's discuss about Databricks notebooks. So Databricks notebooks are collaborative, reproducible, and enterprise ready. They support multiple languages like Python, Scala, SQL, and R all in one notebook, toggling through the different languages. They're collaborative because multiple users can show up with a single notebook. So you and a coworker can edit a notebook, comment things out, and try various things together. So they are great for exploration because they give you things like visualization. Yeah. They are reproducible because they automatically track version history. Alternatively, we can use Git version control and with repos. We can get to production faster because we can quickly schedule notebooks as jobs, or we can even create dashboards from the results all in the notebook. And they are enterprise ready. They have enterprise grade access controls, identity management, and auditability. These are the various features that are offered by the notebooks to us: multi-language, collaborative, ideal for exploration, adaptable, reproducible, get to production faster, and enterprise ready.
Moving to the second topic of our agenda, transforming data with Spark. So, Purva, can you please, yeah. We will talk about the data objects in the Lakehouse. The various data objects are metastore, catalog, schema, consisting of mainly table, view, and user-defined functions. So let's learn about them now. Starting with the metastore. The Databricks Lakehouse architecture combines data stored with the Delta Lake protocol in cloud object storage with metadata registered to our first object metastore. Under the metastore, there are 5 primary objects in the Databricks Lakehouse. The second object is catalog, which is a grouping of databases. The third one object is the schema, which can also be called as database, which is a grouping of objects in the catalog. It contains table, views, and functions. The metal store can have any number of catalogs desired, and similarly, the catalog can also store any number of schemas in it as per the use. We will also learn about these data objects later in our session. So we will talk about the tables. The tables in every schema can either be of two types, either managed or external. A managed table is based on a file which is stored in the managed storage location that is configured to a metastore. When we drop a table, it will delete the table and all the underlying data that we have. Whereas an external table is a table whose data file is stored in cloud storage location outside of the managed storage location. So only the table's managed data is managed. The main functional difference between both the types of tables, managed and external, is that tables become visible when we drop an external table. Here the underlying data is retained and only the table here is dropped. Both managed and external table are otherwise treated the same way from the access control point of view. Now let's learn about the views in a schema. A view is a saved query, typically against one or more tables or data services. The view can further be of two types, temporary views or global views. Finally, we have a function in schema. It is a saved logic that returns a scalar value or maybe a set of rows.
So yeah, moving to the third topic of our agenda, manage data with Delta Lakes. So let's understand what is a Delta Lake. So Delta Lake is an open source storage layer that enables building a data lakehouse on top of existing cloud storage. It is not a proprietary technology or a storage format or a medium or any database service or data warehouse. It is open source. It builds upon standard data formats. While data lakes can be run on different storage mediums, but it is specifically optimized for cloud object storage. Object storage is cheap, durable, and highly available and effectively scalable as well. So it is built for scalable metadata handling. Delta Lake brings asset properties to object storage. Now let's understand what does asset stands for. So A stands for atomicity, which means all the transactions either succeed or fail completely. C stands for consistency, which guarantees that how a given state of the data is observed by simultaneous operation when simultaneous operations conflict with one another. I for isolation refers to the conflict between the operations. The isolation guarantees that Delta Lake provides do differ from other systems. And D for durability is it basically means that the changes that we have committed, they are permanent. Delta Lake is the default format for tables created in Databricks. Whether we are using Scala, Spark, or Python, Databricks makes working with Delta Lakes as easy as simply running a create table statement. So there are 5 major problems which are solved by Delta Lakes using the asset properties feature. First, it was hard to append the data. So it is solved by the consistency property of asset. Second problem was the modification of existing data, which was difficult. So it is solved by the isolation property. Jobs were failing midway. It is solved by the atomicity and durability property of acid. And fourth problem was the real-time operations were hard. So it is solved by Delta Lake, allowing atomic microbatch transactions processing in neural time. And fifth problem was it was costly to keep the historical data versions. So it is solved by the transactional logs that are used to guarantee atomicity, consistency, as well as isolation.
Moving to the fourth topic of our agenda, building data pipelines with delta life tables. So as you can see here, we have the medallion architecture in the lake house. So the first thing that comes into mind is, what are these metal representing here? Are they actually a part of the architecture? So let me tell you, they are the multi hops in the lake house and are just used to make our visualization better about the architecture. It is not mandatory that all the pipelines exactly follow this same model. The reason this model is recommended is that it takes advantage of data lakes, tables, skip transactional guarantees. It also leverages the tight integration between Delta Lake and Spark structure streaming to allow efficient incremental data processing. It provides flexibility to easily adjust data throughput as it requires change with alternates, refactor codes, or redesign pipelines. It creates a fully replayable history of the saved review data system and allows user in the organization to query a common set of validated data state to simplify data discovery and reduce manual time spent on data cleaning. Now let's learn about the multi-hops in the lakehouse. To begin with, let's learn about the bronze layer first. It replaces the old data lake, which was typically a dumping ground for unvalidated data. The main role of the bronze layer is to just get the data into the lakehouse so that the downstream operations can leverage optimization in the delta lake. Data ingested in the bronze layer typically maintains the raw state of the data source and is independent, incrementally grows over time, but may be a batch operation. Retaining the full unprocessed history of each set is an efficient storage format, provides ability to recreate any state of a given data system. Additional metadata may also be added to the data on ingestion for enhanced discoverability. The description of the state of the source data sets are and optimized performance indulging applications. This means that according to time, this data was processed for further evaluation. Now coming to the silver layer. The silver layer represents a validated, enriched version of data that can be trusted for downstream analytics. While Databricks believes strongly in the lakehouse vision, represented by bronze, silver, and gold tables, simply implementing the silver layer efficiently will immediately unlock many potential benefits of a delta lake. For any data pipeline, the silver layer may contain more than one table. The gold layer. The gold layer is often highly refined and aggregated, containing data that will power analytics, machine learning, and production applications. While all the tables in the lakehouse serve an important purpose, gold tables specifically represent data that has been transformed into knowledge rather than just information. Analysts will worthy rely on gold tables for the core responsibilities and will be aware that data shared actual customer routes outside this level. These tables will be completed as a part of the release schedule, production workloads, which help control cost and allows SLAs. While the lakehouse does not have the same deadlock issues that, that we may encounter in a data warehouse, goal tables will often be stored in separate storage containers to help avoid foul limits on data requests. In general, aggregations, joins, and filterings are handled before the data enters into the gold layer. Introducing Delta Life tables. So Delta Life tables are designed to allow users to easily declare batch and streaming pipelines using Python or SQL. Because Python and SQL can be combined with any pipeline, it's easier
No,
than ever.
earbuds ले आइए.
Sorry. Um, Kajal, you are saying something? Okay. So Delta Life tables. So Delta Life tables are designed to allow users to easily declare batch and streaming pipelines using Python or SQL. Because Python and SQL can be combined with any pipeline, it's easier than ever for engineers, analysts, and data scientists to share code and collaborate on production pipelines. DLT has built-in quality control and data quality monitoring features that ensures accurate and useful data built on top of these pipelines. DLT is designed to scale both rapidly growing companies and provides clear observabilities into pipeline operations and automatic error handling.
So moving to the fifth topic of our agenda, deploy workloads with Databricks Workflows. So now let's understand about Databricks Workflows. Workflows is basically a comprehensive task orchestration service that is fully managed and cloud-based, designed specifically for Lakehouse environments. Workflows cater to data engineers, data scientists, and analysts, empowering them to construct dependable workflows for data analytics and AI across various cloud platforms. So Databricks Workflows enables all the data teams to orchestrate any combination of tasks such as notebooks, SQL, ML, machine learning models, and Python code. Furthermore, as workflows sit on top of the Databricks platforms, it can be fully integrated with other services. This allows data teams to use data governance and monitoring services with Databricks Workflows. The team can easily create, run, monitor, and repair data pipelines without managing any infrastructure. So Databricks has two main orchestration services, the workflows, which are also known as workflow jobs, and Delta Life tables, also known as DLTs. So workflows enable all the data teams to orchestrate any combination of tasks such as notebooks, Spark, SQL, ML models, and DLTs. On the other hand, DLTs, they are designed for Delta teams to easily create batch and streaming data pipelines using Python or SQL. DLTs has basically built-in quality controls and data quality monitoring, which ensures accurate and useful business intelligence, data science, and machine learning built on top of quality data. So it is important to note that while these two services serve different purposes, they can easily be integrated into one. So workflows are a little different from DLTs in several ways. First of all, DLT pipelines can be built using only notebooks, while workflow jobs, they can use several different sources such as jars, notebooks, Delta Life tables, applications written in Scala, Java, Python. DLTs can determine necessary dependencies, whereas workflows require that you set the needed dependencies manually. DLTs provision clusters every time when a pipeline is run. Workflows can be self-provisioned clusters when a job is run, or it can be set to use existing clusters as well. DLTs does not support timeouts and retries, nor import libraries, while on the other hand, workflow supports all these actions. Next, moving to the sixth topic of our agenda, which is managed data access with Unity Catalog. So before we dive into the specifics of the Unity Catalog, let's first discuss a more general topic, which is data governance. So a data governance refers to the process of managing the availability, usability, integrity, and security of data. Data governance has become extremely important in today's data-driven landscape, and it needs to establish trustworthy data that is easily accessible to those who need it. When we talk about data governance, we can generally divide the discussion into four main areas, which is data access control, data access audit, data lineage, and data discovery. Let's discuss about all four of them separately. First is data access control. So organizations need to be able to lock down data and data generating artifacts such as files, tables, and ML models. Permissions to access should be granted only to those who need it. Second is data access audit. Any data governance program, it requires knowledge of how data is being used, and that it does not just mean who is accessing the data, but also when and how is our data being accessed and used. Third is data lineage. The journey the data takes from the from the origin as it moves through the pipelines is referred to as data lineage. And being able to trace it is very beneficial in several ways. First, it is much easier to identify the root cause of processing issues. It enables you to predict the impact of proposed upstream changes to your processing. Third, it helps compliance teams to prove that data and reports come from trusted and verified and reliable resources. And finally, it fuels better understanding of data for data analysts, scientists, as well as engineers. Fourth point is the data discovery. Locating data is always a challenge, particularly in a data lake. But a data governance program requires a readably accessible inventory of data assets that can easily be searched. Since the emergence of the data lake paradigm, data governance in this context has been complex. Therefore, we need organizations to employ data lakes alongside data warehouses, which leads to data duplicating and hence data drift. So governance happens at two different levels across these platforms, both of which generally employ one or many different tool stacks. This makes it hard to collaborate and control things consistently. Data and AI governance today is complex. The reason it is such a complex topic is that we have all these different personas on the left, as we can see in the diagram. So we are looking to serve all these type of technologies and we are trying to serve them. And this creates a very complex environment for governance. So in a typical enterprise today, you have a lot of data stored on data lakes. For example, we have AWS S3. To invoke these permissions on the data in the data lakes, you set permissions on files and directories. It means you cannot set find permissions on rows and columns because governance controls are at the file level. Data teams must carefully structure the data layout to support the desired policies. For example, a team may partition a data into different directories by country and give access to each directory to different groups. But what should the team do when the governance rule change? If different states inside one country adopt different data regulations, so then the organization may need to restructure all the directories and files. So it becomes difficult to rewrite all the policy changes. With most data lakes, you not only have files, but you also have to keep the metadata. For example, you might have a Hive meta store that keeps track of table definitions and views. So we must get permission on tables and views. This connection can be out of sync from the underlying data. There's no guarantee that if the user have access permissions on files, then you will have access on the core table or vice versa. So it becomes very confusing to manage these permissions. Then you might have your data warehouse where permissions are more fine-grained on tables, columns, and views. But again, it is a very different governance model. In a typical scenario, basically you have your data movement from data lakes and data warehouses, and now you have created data silos with data movement across two different systems. Each have a different governance model. So as a result, the governance model is inconsistent and prone to errors, making it difficult to manage the permissions and conduct audits or discover and share data. But data is not limited to files and tables. It also has assets like dashboard, machine learning models, and notebooks, each with its own permission model. and tag stack, making it difficult to manage the access permissions for all those assets consistently. So the problem gets bigger when the assets exist across multiple clouds with different access management solutions. What we need is a unified approach to simplifying data governance for data and AI.
Now let's have the overview of the Unity catalog. So by integrating a centralized hub within the Databricks Lakehouse platform for administrating and securing data and auditing our data, Unity catalog rise to these challenges. Firstly, by unified governance across cloud. Unity catalog blends in with the Databricks Lakehouse platform and allows us to define our data access rules once, where they can be applied to multiple workspace, clouds, languages, and use cases, governing all our data assets in a consistent way through easily used user interfaces and SQL APIs. The access control available goes far beyond what any cloud system can provide. Unity Catalog provides access control for all managed data assets, including files, tables, rows, columns, and views. While Databricks has provided some degree of access control in the past, its security model was permissive by default and required careful administration of the access controllers and the compute resources. Accessing the data to yield a fully secure solution, the access control rules are defined as a property of a workspace. So, reliably scaling this out to a multi-workspace or a multi-cloud environment is a real challenge. Unity Catalog fixes all that lives outside the workspace and therefore spans workspaces in cloud. It is secure by default and does not rely on cooperation of compute resources just to enforce access control. Secondly, we have unified data and AI assets. While our data is free to move to roam, Unity Catalog can manage it all from a central hub in a consistent and familiar way. There is no need to replicate or translate our security requirements across different systems. If rules change, those changes only need to be applied once. Unity Catalog also brings with it the ability to do fine-grained auditing of all queries performed to support governance use cases. Data linkage will also be collected and utilized for tables and columns across all languages. Thirdly, we have unified existing catalogs. Unity Catalog is additive and works seamlessly with other meta stores, including the legacy Hive meta stores. It comes with each Databricks workspace, which many of us must have already taken advantage of. Through the three-level namespace, we can have seamless ongoing access to our existing data, while it makes a lot of sense to update our data to Unity catalogs as soon as we can. But there is no hard requirements. Updating data to Unity catalog is a simple operation that can be done anytime we want. Now that we understand some of the benefits that Unity catalogs brings, let's look at some of the key elements of Unity catalog that are important to understanding how Unity catalog actually works. First is the meta store. The meta store is the top level logical container in the Unity catalog. It's a construct that represents the metadata, that is, information about the objects being managed by the meta store, as well as access control. List that governs access to those objects. The Unity catalog meta store is not the same as the Hive meta store. The Hive Meta Store is the traditional default Databricks link to each Databricks workspace, and while it may seem functionally similar to Unity Catalog Meta Store, Unity Catalog Meta Store offer improved security, auditing capabilities, as well as improved security model and a host of other features. It's best to think of Metastore as the logical construct for organizing our data and its associated metadata rather than a physical container itself. This seems reflective in the physical makeup of Metastore, and accepting this idea will also make some of the best practices more sensible. The meta store essentially functions as a reference or a collection of metadata and a link to a cloud storage container. The metadata, that is information about the data objects like tables, columns, data types, for example, as well as the access control list for those objects, is stored in the control plane. This ties the meta store to a cloud region. This is why account administrators are prompted for a region when creating a metastore. Data-related objects managed by the metastore are stored in a cloud storage container, which is also configured as a part of metastore setup. An important property of Unity Catalog is that it is additive and does not produce access to our existing data objects stored in our local metastore. Once a workspace is connected to Unity Catalog through assignment of Unity Catalog Metastore, Unity Catalog represents the Hive Metastore as a special catalog named Hive underscore Metastore. Assets within the Hive Metastore can be seamlessly referenced by specifying the name Hive underscore Metastore as the first part of three-level namespace, or if set as the default catalog, two-level reference works as they always have. Of course, Unity Catalog will never enforce any access control over assets stored there. The legacy table access controls are supported in some compute configurations. With the high-level understanding of what is a metastore, let's now drill into the data objects hierarchy, starting with catalog. A catalog is the topmost container of data objects in the Unity catalog and forms the first part of the three-level namespace. Metastore can have as many catalogs as desired. Catalogs are the containers, but they can only contain schema, which we will talk about next. The concept of schema is sometimes referred to as database, is a part to traditional SQL and is unchanged by Unity catalog. Its function as a container for a data bearing assets like tables and views, and forms the second part of the third level namespace. Catalogs can contain as many schemas as desired, which in turn contains as many objects as desired. At the bottom layer of the hierarchy, let's first talk about the tables. These are SQL relation consisting of an ordered list of columns, and overall concept of it is unchanged by Unity catalog. Although tables do have variations in Databricks, and to fully understand, it is important to recognize that tables are defined by two distinct elements. First, the metadata or the information about the table, including the list of columns and their associated data types. And then we have the data that populates the rows of the table originating from data files stored in cloud storage object. As we have earlier discussed in the session, tables can be of two types, managed and external. Now let's talk about views. They are essentially stored queries that are executed when we query the view. View perform arbitrary SQL transformation of tables or other views which are read-only. They do not have the ability to modify the underlying data. The final element is the data object hierarchy. Our user-defined functions or UDFs. They enable us to encapsulate custom functionality into a function that can be invoked within queries. We also have the storage credentials and the external location. Let's talk about storage credential first. Since all the data lives in the cloud Unity catalog, Unity catalog needs a way to authenticate with cloud storage container. This is true whether we are using the default storage location configured as a part of Metastore or the arbitrary user supplied cloud storage. The storage credential satisfies the requirements of encapsulating an authentication method to access cloud storage. Each Metastore has access to external cloud storage to support external tables or file access. While storage credentials fulfill the critically important requirement, they are not very convenient in terms of access control when dealing with external cloud storage. Storage credential applies to the entire cloud storage container, their reference. Therefore, granting privileges on them apply to either container. It's typically desired to achieve fine-grained control. Moving to external locations, they are built on the concept of storage credentials and extended with storage path with the cloud storage container, allowing users to arbitrarily subdivide containers into smaller pieces and exercise control over each subdivision. External locations can be used to support and manage external tables. They can also be used to govern direct access to files stored in cloud storage. Finally, we will talk about shares and recipients. Both of these relate to delta sharing, an open protocol developed by Databricks for secure, low overhead data sharing across organization. It is built in Unity Catalog and is used to explicitly discuss shares, that is a read-only logical collection of tables. These can be shared with one or more recipients, that is a data reader outside the organization.
So the last part of our knowledge is the Unity Catalog architecture. So after having discussed about the key concepts of Unity Catalog, let's discuss about its security model in action. So let us begin with touring the life cycle of a query to see how Unity Catalog provides access control in a secure yet performant way. The story begins with the principal issuing a query, which can be issued through all-purpose clusters for cases when users are running Python or SQL workloads interactively. In the case of a job or a pipeline running as a service principal, this will typically run through the job cluster. Alternatively, data analysts can issue queries in Databricks SQL through the SQL warehouse. In any case, the applicable computing source begins processing the query. Next, the request is dispatched to the Unity catalog, which in turn logs the request and validates the query against all the security constraints defined within the metastore to make the computing resources associative. For each object reference in the query, Unity catalog assumes the appropriate cloud credentials governing that object as provided by the cloud administrator. For managed tables, this could be cloud storage associated within the metastore. For files or external tables, this could be external location governed by the storage credential. Again, for each object referenced in the query, Unity Catalog generates a scripted temporary token to enable the client to access the data directly from the storage and return that token along with the access URL. This allows the cluster or the SQL warehouse to access data directly and securely. The cluster or the data warehouse requests the data directly from the cloud storage using the URL and token passed from the Unity catalog. Data is transferred back from cloud storage. This request process is repeated for each object which is referenced by the query with access to data at the partition level. Last now, the column-based filtering is applied on the cluster or the SQL warehouse. And finally, the filtering results are passed back to the column. So that's all. Thank you everyone for joining the session.